You are standing in the middle of a chaotic city street, surrounded by sirens, construction, and thousands of overlapping voices. When you make a phone call, the person on the other end hears you perfectly clear. While we often credit artificial intelligence for this clarity, the process is mechanical. Stripping away that background chaos requires intense, real-time mathematics. Digital signal processing is the specific engineering field that handles this. It provides the framework for continuous data manipulation, separating your voice from unwanted frequencies. To see exactly how this works, look at the entrance exams for institutions like the Indian Institutes of Technology. These papers test specific integration rules because they are the literal algorithms used to isolate audio signal from noise. These calculus rules function as a physical filter. They provide the mechanical logic that makes modern digital communication possible. This diagram shows the raw audio input of a phone call, a messy waveform defined by jagged peaks. Engineers use Taylor series expansions to approximate these fluctuations, tracing the chaotic signal to convert it into a manageable, infinite geometric series. Once the signal is mapped, the Newton-Leibniz rule is applied. This allows the processor to measure the exact rate of change across specific, defined limits. These rules have provided the strict logic required to measure continuous change since the 17th century. These foundational tools translate unpredictable real-world chaos into a continuous mathematical function that a digital processor can finally read. Now that the wave is readable, the computer must distinguish the human voice from the random background garbage. Engineers use King's rule, exploiting mathematical symmetry to isolate data. Human voices follow patterns, but noise is random and asymmetrical. Applying King's rule forces symmetry onto the wave across positive and negative bounds. The noise is added against its inverse, optimizing to zero, leaving clean audio. By weaponizing mathematical symmetry, processors instantly delete audio garbage without needing to individually analyze thousands of microscopic sound waves. This optimization technique scales far beyond making phone calls sound clearer. Because atoms and molecules possess structural symmetry, physicists can apply these same integration shortcuts in quantum mechanics. By focusing on symmetrical regions, they can accurately locate an electron, collapsing a cloud of probability into a defined, glowing sphere. Machine learning algorithms also rely on these shortcuts to build efficient system models without the need for exhaustive point-by-point data analysis. Across all these fields, the primary value of these calculus rules is time. They save supercomputers thousands of hours of brute force processing. This brings us back to the elite university classroom and those difficult advanced calculus papers. Solving these problems requires more than the rote memorization of 17th century rules. These exam questions function as micro-simulations, testing whether a student can master the fundamental language of system optimization. Finding the area under a curve serves as the training ground for building algorithms that manipulate digital reality. Those daunting, abstract equations are the invisible, high-speed engines keeping our digital world clear of the noise.